kind of nice because we get to the point where we're actually talking about things that people usually associate with astronomy, mainly telescopes. Talk about different designs of telescopes and different instruments to get utilized to make observations. But I'm just going to review a little bit from chapter 4 before we move on to the key material. Okay, so we talked about atomic structure and how it gives rise to the patterns and lines of a continuous spectrum, emission spectrum, bright line gives dark background, and absorption spectrum, dark line against it. That is the continuous background. And again, for a given substance, we're seeing the lines of the same wavelength of their emission or absorption. Right, so I'm just going to go over Kirchhoff's laws again because we did that at the end of the last lecture. We have hot gas at a high density or pressure. It's going to glow with continuous spectrum. So you see hot gas can do two different things depending on whether it's dense and high pressure or not. If it isn't high pressure, then what you're going to find are continuous spectrum because of the fact that you have free particles involved and you don't have discrete energy levels. Without the discrete energy levels in an atom, you don't get those lines. Instead, you get a continuous spectrum. So the first law is that hot gas at high density or pressure is going to give you the continuous spectrum. But the second law, again, applies to the situations that we talked about a lot involving hot gases at low density pressure. You have a rather thin, low density hot gas, then what you're actually going to produce is emission lines. And we've kind of discussed this several times, but again, just to reiterate, the basic mechanism involved here is that you have a hot gas that's not so hot that the atoms are actually bumping each other apart, but they're colliding with enough energy to cause excitation. And the excitation is followed by spontaneous radiative de-excitation, and those photons escape. So this process is going to result in the cooling down of the gas. And what we're going to have is the kinetic energy of the thermal motions converted into light energy at specific wavelengths, not a continuous spectrum, but a discrete emission line spectrum. Let's go over the panels that we use in the book to discuss this. If we have a hot bulb with a hot filament, we're going to get a continuous spectrum, no absorption lines, just a straight continuous spectrum. If we heat hydrogen gas, now this is clearly at low pressure, because we're seeing emission lines over there. This is hydrogen heated at low pressure. If it was very dense, high pressure hydrogen, we would actually see a continuous spectrum over there on that screen rather than a emission spectrum. Okay, so this is the third law, which has to do with the creation of absorption lines. So this is again one of my little dramatic creations of one of our former commander chiefs there. And let's see what happens here. We start off with hydrogen in the ground state. Okay, so this green photon, I really shouldn't take up the red, but anyway, it causes excitation. Now he's expecting the green photon to come through. He learned in his maturity briefing that morning that the green photon was supposed to come through, but it's been intercepted by this hydrogen atom, which gets excited and then emits in another direction. And
the terrorists are kidnapping photons.
I'm not sure if you heard what he said there, but he thinks that terrorists are kidnapping our photons, and then a little bit of a, I want to take a little bit of physics there. But anyway, so it's not terrorists kidnapping photons, it's rather photons causing excitation, leading to de-excitation, and then of course the reason that George didn't see the photon is because it went in some random direction, right? So from his point of view, he would actually see an absorption line if he plotted the spectrum that he sees. Because many wavelengths would make it through, but not the ones that actually lead to the excitation of the atom. All right, so same thing again. Hot bulb illuminating a cool gas, absorption lines. And of course we know that what's really going on is that there's lots of photons that are resulting from the de-excitation, but most of them are just going in three-dimensional random directions. Very few get through the slit, and so we end up with this lack of photons that causes the absorption line. So again, the unified model figures in the book has almost everything in it, just doesn't have anything to do with hot gas. Right? We see that if we back illuminate cool gas, we get absorption lines. If we view the cool gas from the side, we see an emission spectrum because the only photons that pass through this slit is just a tiny fraction of the de-excitation photons. It's only a tiny fraction, but that's all the photons that go through the slit. So you actually do see an emission spectrum. send light through, the white light source into a cool gas. Many wavelengths make it through, but you see here the red, very few photons are emitted in the original direction. 99.99999% go in other directions. But down here, all we receive are some of those emission line photons, so that's why we see that emission spectrum. All right, I also am going to review what we discussed about the Doppler shift, because one of the reasons that atomic spectra are so important is that not only can we use spectra to identify the composition of a distant source. So this is one example of what we call, remote sensing. I mean, it's also used looking down on the Earth, for that matter. NASA has lots of satellites that look down on the Earth and analyze radiation coming off, green living things. And from the patterns of lines in those spectra, they can determine, the species of tree they're looking down at, and even its health, things like that. So it's not just astronomy; it's kind of remote sensing in general. This idea of using spectra to analyze the composition or properties of what you're looking at. So anyway, once we recognize the pattern, we know the composition, like this hydrogen right here, but because the wavelengths don't actually correspond to the laboratory spectrum, you see, we just see the hydrogen gas in the laboratory, then we know that this is a case where the source is receding away from the observer because of this redshift. An increase in wavelength compared to the lab spectrum that you would see if you were at rest with respect to the source. So again, I'm just going to go through this because I only went through this once and it's a little bit mathematical. We can actually compute the velocity of the source by combining the observed data with the information about the laboratory emission that we know from making laboratory observations. We can make a little table of the observed wavelength versus the emitted wavelength. And the observed wavelengths are all a little longer than the emitted wavelength. So we know qualitatively the source is moving away from us. So again, on an exam, presented with this kind of thing, you'd be asked to calculate the velocity. So the first quality control thing to do is realize that it certainly has to be a positive velocity because positive velocity is moving away from you. And this is a redshift situation for sure, because you see the observed wavelengths are longer than the emitted wavelengths. Definitely a redshift. We must have the source moving away. So what we do is we compute the velocity by taking any one of these observed wavelengths and dividing by the emitted wavelength. So that's like divided by this lambda emitted. And that will isolate this 1 plus v over c term. So when we do the math using the table, we find that lambda emitted observed over lambda emitted is 1.058, and that has to be equal to whatever's left on the right-hand side, which is just 1 plus v over c. We carry through the algebra and we find that v, right there, we subtract 1 from both sides, we get v over c is 0.058, so v is 0.058c. If you made a sign error, you might come up with a negative, maybe. If you make a sign error and you come up with negative 0.058c. But you know that was wrong, because it has to be a positive velocity, because we already know it's a redshift. So you can do a qualitative check on your result and realize that, okay, I know it has to be positive, so if you somehow come up with the wrong sign or something, then you'd be able to detect that and correct your answer. All right, now this is getting into something that we didn't talk about last time. Not only can we have very sharp emission and absorption lines, which would, if we plot the spectrum, a sharp emission line is going to be a big peak at a certain wavelength and then flat. So you come along flat, big peak, move along, another big peak. But there's a question about how wide those peaks actually are when we plot the spectrum. They can be very narrow, or they can be observed to be more broad. So we're going to talk about mechanisms that can lead to an emission or absorption line being a broadened feature. So instead of being a spike, being a broader kind of bell-shaped curve, if we make our standard plot of brightness when we're talking about a spectrum. All right, so it all comes down to the relative velocity of the atom that's emitting with respect to the observer. So we just said that if the star is receding away from us, we just get a shift. But it can be a little more complicated than that, because stars, after all, are made of many, many different atoms, and we can have other effects involved, which can be thermal effects or positive effects related to the rotation of the star. All right, so if we have the atom at rest, we might see this blue wavelength here. If that particular atom is emitting but is receding away from us, we're going to see a reddish redshift. If that particular atom, same substance, but if the emitting atom is moving towards us, we see the blue shift. So this is the Doppler effect. Now, as I said, this enters into the broadening of an emission or absorption line in two ways. So the first thing we're going to look at is the thermal effect. Now, if all the atoms were all moving away from us, for that star example, if all the atoms are moving away from us, we just see a perfectly sharp emission line because they'd all be doing the same thing. But the thing about stars is that they actually have very hot atmospheres. So on top of the motion of the star, you also have random motions of the atoms, in the atmosphere of the star because it may be 6,000 kelvins. It's very rapid motion. So when we look at the stellar atmosphere, we're looking at a hot gas that the entire thing may be moving away from us or towards us, but on top of that systematic motion, you also have this thermal motion. And the thermal motion means that you can have some of the emitting atoms moving towards us, some of the emitting atoms moving away from us. Now these are all identical atoms doing the same thing in their own rest frame, but from our point of view, they look like they're doing different things. The atom that's moving towards us here, when it decays, is going to produce a photon which would appear to be blue shifted. An atom moving away from us, like this one right here, would produce a photon which would appear to be redshifted. So even though they're all the same atoms doing the same thing, the observer over here is actually not going to see a perfectly sharp line because he's going to see a component that's associated with atoms that are moving towards them, which is the blue shift side over here, and he's going to see components due to atoms that happen to be moving away because of this random thermal motion. Now you notice there is a peak, and that's simply because you have a certain average thing that atoms are doing. So the sort of average thing that they're doing is going to contribute to this peak right here. Now the width of this thing is actually going to be related to the temperature. Because let's think about, let's do a little thought experiment here, okay? So there's some temperature associated with this particular feature, and that's creating some preponderance of atoms that are moving towards the observer, some moving away. But suppose we cooled it down. We could turn the temperature dial down and go all the way down to absolute zero, let's say. There's no thermal motion anymore. All of the atoms are just sitting there. All these sort of vectors here, they all go away. You just have dots all over the place, right? And then according to the observer over here, they're just going to see the same thing for every atom in that case. So you won't see any width at all, and it'll just be a perfectly narrow line. So the point is that the width of the line you see is actually going to be related to the temperature. It's going to be broader the higher the temperature is. So this is what we call thermal broadening. And it's one way in which the Doppler shift can cause broadening. One of the two mechanisms we'll talk about. So again, if we look at a curve of intensity or brightness here, we see contributions at longer wavelength, which is due to the atoms that happen to be moving away from the observer, contribution at shorter wavelengths due to atoms that are approaching the observer. Okay, so that's thermal broadening. You're going to have a broader emission or absorption line. It works with both kinds of lines. Now, it'll be broader as you crank up the temperature. But there's another thing that can happen. Suppose the star is rotating. We already kind of talked about this a little bit because I mentioned that when we look at black holes and we see certain features that are really redshifted and blue shifted, that's our best evidence for black holes because it implies super high orbital velocity, close to the speed of light. Well, if you just look at a star, these are kind of ordinary velocities, not anywhere near the speed of light. But you do still have part of the star approaching you and part of the star receding away. So if the star is covered with atoms that are doing the same thing, let's even suppose it's a cold star, so we can forget about the thermal thing I was just talking about. Just suppose it's cold and you just have the same atoms all over the star. Well, the observer over here is not going to see a precise narrow line because the observer is going to see a mixture of things that are created at different parts of the star that are all mixed together in the observation. We can't look at any star right now and just look at the center or at one edge or the other because stars are so far away compared to their size that they have sizes of millionths of an arc second. We can't do that. So when you look at any star except the sun, you're seeing the mixture of everything that's being produced on that star. So the observer over here is not going to see a narrow line because they're going to see contributions from all parts of the star that have different velocities. So the end result of this is that you actually get a broad curve like this.